Hello everyone. Let's take a look at this circuit. So what you see here is a very well known circuit. So let me explain slightly. So you have 12-volt power supply here, and then you have Zenar diode, and its Zenar voltage is 5 volt, and you have a typical safety resistor here, and then this is your load. So for example, the load could be your application. This could be your mobile phone. So your mobile phone requires 5-volt supply, and you have a car battery that is 12 volts. So having this kind of regulator circuit, you can uh, convert this 12 volts into 5 volts, and you can provide that to your mobile phone. Uh, in this circuit, uh, this side you have the regulator. Actually, this is the regulator circuit. You have safety resistor and diode, and then you have this application that is your mobile phone. In this case, it's a load resistor, and importantly, we're having a regulator circuit like this. What we expect a regulator circuit like this, what we expect is even if our input changes, output voltage, we need to maintain that in a constant level. So theoretically, what we expect over here is over here is 5 volts, whatever the value you have. Right. So you can do okay. So you can connect circuit like this, and you can measure voltage here, and you obtain 5 volts. So then you need to see what will happen if input change. Okay, you can change this one to 11 volts and see what will happen to the output. Or maybe you can change it to 7 volts and see what will happen to this one. Or you can change it to 15 volts and see what will happen to the output. So all the time, if we use our terminology, we have fixed voltage, let's say it's 15 volts, and we look for the voltage across this one. So that is what we call a bias point analysis. Now this bias point analysis you need to do for different voltages. So the parameter over here is the voltage of this power supply or the battery. We change it to different value. While changing this one, we measure uh, uh, voltages or currents or even power dissipation through different points of our circuit. So this is what we call DC sweep, and having a tool like OrCAD, you can do it automatically. You can provide set of values, and automatically system will sweep through this, and we can get the appropriate output. So let's take a look at, let's jump to OrCAD and see what we can do. As usual, let's start a new project. We'll go File, select New, and we will select New Project. And there we can put some name for our project. And then you have 4 different options. Out of 4 different options, if you want to do the simulation, you need to select this one, and I'm going to save my file in this location. So and I want to create a brand project. So now what I'm going to do is, first I will draw a schematic diagram here. So if you want to learn more about this one, you can view my first video in this series, that is for the bias point analysis and how to place the component. Anyway, I will do everything over here. You can follow it from here also. So in order to first insert elements, now this area is basically your working area, and in order to place element, so you need to select this place part object. The shortcut is P. Now one thing, as I always mention, uh, so you might be doing different project with this one. Whenever you start it, it's always good to remove all the libraries. The reason to remove all the libraries, and then I will add libraries which belong to the Pspice. So this is my path. So I'm using libraries under Pspice. So with there are a lot of different types of libraries are compatible with OrCAD suite, and even with capture sys. So, but the libraries specifically made for Pspice, they come with their own mathematical model. There may be certain libraries which might have the footprint, but not the mathematical model to do the simulation. So if you have inserted that kind of component, you might not be able to do that. So therefore, always make sure you remove all the libraries and add all the Pspice libraries there. Okay. So we will start adding components. So I will search VDC, that is my power supply, press enter and place my power supply here. Then I need two resistors, R, press enter, and here I will place it in this orientation. Then the load resistor I will rotate. So rotation you can do with R. So I'll press R and I rotate it and I'll place it here. Then I need Zenar diode. So I will select whatever Zenar diode available. So I will select 1N4099. So to be frank with you, I don't know what the Zenar voltage of this one. So we will do the simulation and see actual uh, Zenar voltage of this device. Right. So we have almost required all the components, and we now we can do wiring. So in order to do wiring, you can use this tool. The shortcut is W. So I press W. So my mouse pointer now change to wiring tool. Right. So I have finished my wiring, but remember there's something missing here. So since we are going to do measurements on voltages, always we need to have a reference. So in order to get reference, so we will put ground wire here. So there's a tool called ground, and that tool you can get it from by pressing G if you want. And from that I will select capsin. So that is the reference. So this is my 0 voltage source. So that from this I'm going to measure. All my measurements are based on this reference voltage 0. Right. Now we are good to go. So we'll start with creating simulation profile. So I'm going to create new simulation profile. I can uh, give some name to that and I'll create it. Then another dialog box will appear shortly. In this dialog box, I need to select. So these are the different options. So I want to select DC sweep. So DC sweep, basically you can see here you have primary sweep and secondary sweep. So if you want, you can sweep two parameters one after the other in nested way. And if you go for the basic options, primary sweep, so there are like different options you can select. You can sweep voltages, current, or some global parameters, model parameters, or temperature. So different things you can change it. So I'm going to change the voltage of this voltage source. So I will put the voltage source V1, that is the name of the voltage source, and I'm going to do a linear sweep, and my starting value uh, I'll select maybe 2 volts, and end value I'll select 20 volts, and increment the step size I will select 0.5, since I'm doing it for the first time. So when you put 0.5, my resolution is not that high, but the time taken to do the calculation is very less. So I will use that first, and then now I'm ready to do the simulation, but I will do few more changes. So since this is safety resistor, I will put small value like 20 ohms, and the load resistor I will change that to maybe 100 ohms, and this one actually I'm sweeping, but just to get some nice idea, I will put 12 volts there. Right? Anyway, I'm changing this value to different values. Right. Okay. So then I would like to use one of these voltage level markers. So I'm going to use this one and put it here. So that one advantage is that when you put it there, I'm getting graph automatically in this data. Right. So then I'm going to run the simulation. So this is run Pspice button. So when I click it, this will start doing the mathematical calculation, and shortly I will get another window. From that I will be able to see the output from this one. Right. Now what you can see in this diagram, so let me put it in side by side. Uh, in fact, I can increase the trace size. Uh, okay, I'll increase the width so that it's more visible to you. So this is how it works. This x-axis is V1, that is voltage at V1. So that is this one. I'm changing that from 2 volts to 20 volts. So as this voltage increases at roughly about here, it's getting saturated. So this is 4, 2, 3, 4. It's like about 7 volts. So at 7 volts, it's clamping. So basically this regulator, it's settling its voltage at 7. And if you want to do high resolution one, you can do that kind of simulation, but this one is getting saturated here. Apparently it's kind of nice. Right. So then this is fine. So we sweep this one and get the output. So if you want, we can go one step further and do a little bit of more simulation. So for that, I'm going to remove this. And these wires also I will remove. Right. So now I have this circuit. So this is here I have Zenar diode, and I have voltage source and a safety resistor here. So by using this circuit, I can try to obtain VI characteristic curve of this diode. Uh, so in if you I'm sure you remember what VI characteristic curve is. Anyway, I will just draw it here. In VI characteristic curve, our x-axis, we have two axes. So in VI characteristic curve, our x-axis is voltage across the diode, and y-axis is current through the diode. So this curve looks like this. Till once you reach your barrier potential, it will increase this, and when it is reverse bias, it will go like this, and after certain voltage, that is the Zenar voltage, it will start conducting in reverse bias mode, and this is what we call the Uga effect. Right. So let's try to obtain this curve. So remember that we need to have current and voltage across the diode. Let me clear this drawing. Right. So in order to get this done, what I will do is I will do the same simulation, but now I will change the range. Right. So this is edit simulation button. I can edit existing DC sweep, and now I'm going to sweep it from my starting value is minus, say, minus 10, and my end value is plus 10, right? And my increment, the step size, I will go for a little bit of higher resolution. I will go with 0.1, or even I can go with smaller 0.5 step size. So I'll press OK. Then I'll run this one. Now in this time I haven't put any markers here. So when I get this simulation finished, this is what I get. So basically voltage source is changing from this direction, that direction, nothing else. So I can add different traces here. So if you remember, our y-axis has to be current through the diode. So I will add the trace. I'll go to trace menu, and from there I'll select add trace. And then there are different options. I can select uh, currents. I have current through the diode. Uh, I will select the first one. So, when I click this, it comes here. So this is the equation. So if you want, you can like have connect different things and get it done. For the time being, y is the current. Now this graph, basically what you have in this axis is current, and this axis is voltage V1. So that is not what we want. What we want is voltage across the diode. So we want to change the variable used in x-axis. That we can do. We go to plot menu, and from there you select axis settings, and then x-axis we have this button. From this we can change the variable. So what we want is the voltage across this diode. So for that I will select voltage. Okay, there are different options. So here I have voltage at anode and voltage at cathode. So I will measure voltage at anode minus voltage at cathode. Actually voltage at cathode is 0 now, right? Anyway, you can have equations like this. I'll click OK. Click OK. Right. Okay. So maybe I'll increase the visibility of traces. I'll go to a trace property, and from there I will select little bit of thick. Right. Now you can see this is the voltage across the diode. So I change it from roughly about 7 to 2 volts, and the current. So actually the voltage is basically limited to this range. So the rest of, even if I try to increase the positive or negative voltage, rest will be remain in the safety resistor. So you can see that. So here it is about so this is 0, about 0.65 you get this current conducting uh, section. And also when you reverse bias it, about 6, and at 7 actually you are getting this one. So if you want, so I'll put this full screen. If you want, there are different options you can explore this graph. So you can select there's a button called toggle cursors. So I can select cursors from this. So my left mouse button, so when I move I get one cursor, and when I use right mouse button I get another cursor. You can see it, right? And the values of those cursors, they are available here, y1 and y2. Even I can take the subtracted value from y and y2. So I will go here and put it here. Now you can see, now when I'm going here, it's going through the curve, right? So if I'm there, I get both x and y readings for this particular point. So it's a red cursor now I'm using. It's, and okay, I'll take the other cursor over here. Right. So I have a red cursor and green cursor. Right, okay. So I collapse everything. So now you can see as I change one cursor, so the now I'm changing red cursor, right? So red cursor value is changing. Now it is like 2, 3, and I'm reaching here. Now red cursor value is, you can see, is 6.28. So that is the barrier potential for this particular diode. And if you look at the other cursor, the green one, so I'm changing it here. So So the green cursor value is minus 6.951. So that is the reverse the Zenar voltage of this diode. Hope you learned something from here. So see you in next video. Thank you very much.